On August 25, 2012, Voyager 1 became the first human-made object to leave the sun's protective bubble and enter true interstellar space. Every instrument on board confirmed it. The density of charged particles jumped by a factor of 40. Energetic solar particles all but vanished, and cosmic rays from beyond our solar system surged. By every measure that mattered, Voyager 1 had crossed the boundary. It was gone, out in the space between the stars. For a spacecraft launched in 1977, designed with a primary 5-year mission to study Jupiter and Saturn, reaching a genuinely new region of space that no human-made object had ever sampled before was already an extraordinary achievement in its own right. But almost immediately, one specific piece of that achievement refused to fit cleanly into the story scientists expected to tell. Except one instrument disagreed. The spacecraft's magnetometer, the device measuring the direction and strength of the surrounding magnetic field, showed almost no change at all. Scientists had confidently predicted that once Voyager 1 crossed into interstellar space, the magnetic field around it should rotate dramatically, swinging away from the sun's own magnetic signature toward a completely different orientation, one belonging to the wider galaxy rather than our own star. Instead, the field barely budged. It looked, for all the world, like Voyager 1 was still sitting inside the sun's magnetic influence, even as every other piece of evidence said it had left. More than a decade later, this specific contradiction still hasn't been fully, cleanly resolved. Multiple competing theories have been proposed, tested, and refined. Some researchers have gone so far as to argue the discrepancy means Voyager 1 technically hasn't left the heliosphere at all, a genuinely controversial minority position within the field. This is the story of one of the strangest, most persistent puzzles in modern space physics. How can a spacecraft be unmistakably outside the sun's bubble, while the sun's own magnetic fingerprint still seems to be stamped all over the data? This isn't a manufactured mystery dressed up for a thumbnail. It's a genuine, still actively published scientific disagreement playing out across more than a decade of peer-reviewed papers, involving some of the same physicists who first predicted what the crossing should look like, still working today to explain why it didn't match their own expectations. To understand why this mystery is so genuinely strange, you first need to understand exactly what the heliosphere is and why scientists were so confident about what should happen at its edge. Our sun doesn't just emit light. It also constantly streams out a flow of charged particles called the solar wind, along with its own magnetic field, both of which extend far beyond the planets, inflating an enormous invisible bubble around our entire solar system known as the heliosphere. Inside that bubble, the sun's magnetic field dominates, generally organized into a predictable, spiral-shaped pattern called the Parker spiral, named after physicist Eugene Parker, who first theoretically described it in 1958. Beyond the heliosphere lies interstellar space filled with material from other stars and shaped by an entirely separate magnetic field, the interstellar magnetic field, that scientists expected to point in a noticeably different direction than the sun's own field, since there was no obvious reason the two should happen to align. The heliosphere itself isn't a perfect, symmetrical sphere either, as our entire solar system moves through the surrounding interstellar medium at roughly 5 kilometers per second. That motion compresses the heliosphere on the leading side, while stretching it out into a long, trailing tail on the opposite side, giving it an overall shape scientists often compare to a comet, or sometimes described as more of a deflated croissant, based on more recent modeling. That asymmetry matters for this story because it means the expected direction of the interstellar magnetic field relative to the sun's own field was never expected to be a simple, uniform relationship. It depends on exactly where along that irregular comet-like boundary a spacecraft happens to be crossing. Voyager 1 and Voyager 2 launched in 1977, and after their famous flybys of Jupiter and Saturn, both spacecraft continued outward, specifically tasked with searching for the edge of this solar bubble. Voyager 1 would have crossed the termination shock, an inner boundary where the solar wind abruptly slows down, in December 2004 at a distance of 94 astronomical units from the sun. It then spent years traveling through the heliosheath, a turbulent transitional region, before finally reaching the heliopause itself, the true outer edge of the sun's influence, where the solar wind's pressure finally gives way entirely to the pressure of the interstellar medium pressing back from outside. The journey through the heliosheath alone took nearly 8 years, and it wasn't a smooth, predictable passage. Voyager 1's low-energy charged particle instrument recorded the intensity of energetic particles from the sun beginning to steadily decline starting in 2011, as though those particles were gradually leaking outward into interstellar space ahead of the spacecraft itself, while the outward speed of the solar wind measured near Voyager 1 slowed to essentially zero. According to Matthew Hill, a scientist working on that instrument at Johns Hopkins University's Applied Physics Laboratory, the team had grown confident enough in this pattern that, based purely on those particle measurements alone, They would have argued the spacecraft had already crossed the heliopause a full year before the date now officially recognized. But without functioning plasma instrumentation to independently confirm exactly when and where that crossing occurred, the team had to rely on the magnetic field data as a secondary check. And that's precisely where the trouble started. Based on theoretical models built up over decades, physicists expected the magnetic field direction to change dramatically right at that crossing point. A clear, unmistakable signature that would let scientists say, with total confidence, this is where the sun's influence ends and interstellar space begins. Voyager 1's other instruments gave scientists exactly the confirmation they were looking for, but its magnetometer told a very different story. Let's walk through exactly what Voyager 1 recorded during that crossing, because the details matter enormously to understanding why this puzzle has proven so difficult to resolve. On July 28, 2012, Voyager 1's instruments picked up the first hint that something significant was happening. The intensity of galactic cosmic rays, high-energy particles originating from far outside our solar system, abruptly jumped, while the concentration of solar origin particles began plummeting. At the same time, the strength of the local magnetic field doubled, reaching about 4 nanotesla. Over the following month, the spacecraft recorded 4 more similar inflection points, an alternating pattern of the field weakening, then jumping, then weakening again, before a final decisive jump on August 25, 2012, now recognized as the official date of Voyager 1's crossing into interstellar space. That specific timeline already hinted at something more complicated than a single, clean boundary crossing. But the truly puzzling part came from the magnetic field's direction, not just its strength. According to physicist Leonard Berlage and colleagues who published the original analysis, the magnetic field's angle barely changed at all across the crossing, even though its intensity clearly increased. Based on independent measurements from other spacecraft studying the wider heliosphere from a distance, scientists had a reasonably confident prediction for what direction the true interstellar magnetic field should point, and it was expected to differ substantially from the Sun's own Parker spiral orientation. Voyager 1's data showed nothing of the sort. The field it measured looked remarkably similar in direction to the solar magnetic field it had been sitting inside for decades. This wasn't a subtle, easily dismissed anomaly. It directly complicated the very definition of what had just happened. Voyager 1's particle data screamed, "You have left the heliosphere." Its magnetic field data whispered, "But the sun's fingerprint is still all over this place." Compounding the difficulty, Voyager 1's plasma instrument, the device specifically designed to directly measure the density, temperature, and speed of the surrounding charged particle soup, which would have offered the clearest possible confirmation, had stopped working years earlier, forcing scientists to rely on indirect methods and an unusual stroke of luck, a solar outburst that happened to rattle the surrounding plasma just enough to let researchers infer its density indirectly to help make sense of what was actually happening around the spacecraft. For 6 years, Voyager 1 was the only data point scientists had for this exact question, which left open the possibility that its strange magnetic readings were simply a one-off coincidence, or some kind of instrument-specific quirk, rather than a genuine feature of the boundary itself. That changed in November 2018, when Voyager 2, trailing behind its twin, traveling through a different part of the heliosphere's southern hemisphere, crossed its own heliopause boundary. Crucially, Voyager 2's plasma instrument was still fully functional, giving scientists their first direct, unambiguous plasma density measurement right at the moment of crossing, rather than relying on indirect inference the way they'd had to with Voyager 1. And when researchers checked Voyager 2's magnetometer data, they found something that made the mystery even more interesting rather than resolving it. The magnetic field just beyond Voyager 2's heliopause crossing was oriented essentially parallel to the field on the inside. The same fundamental puzzle Voyager 1 had presented 6 years earlier, now independently confirmed by a second spacecraft in a completely different part of the sky. That confirmation ruled out the possibility that Voyager 1's readings were some kind of isolated fluke, and made clear that whatever was causing this effect was a genuine, repeatable feature of how the heliosphere's boundary actually behaves. In the years since 2012, several serious, competing theoretical explanations have been proposed to make sense of this contradiction. And it's worth walking through each of them honestly, because none has achieved complete, unanimous acceptance across the field. The first major explanation came from Boston University physicist Merav Ofer, working with colleague James Drake. In late 2013, they ran detailed magnetohydrodynamic simulations, computer models of how magnetic fields and charged particles interact, and found that as the true interstellar magnetic field approaches the heliopause, it doesn't simply meet the solar field head-on. Instead, it drapes and twists around the heliosphere, somewhat like an elastic cord stretched and wrapped around a beach ball, picking up a component of the sun's own field orientation in the process. Under this model, the field Voyager 1 actually measures near the boundary reflects this distorted, muddied transitional region, not the true, undisturbed interstellar field, which the model predicted would only reveal itself gradually at increasing distances further from the heliosphere. A related 2015 study built on this framework and made a specific, testable prediction. If the field continued steadily rotating as expected, Voyager 1 should finally observe the true, undistorted interstellar magnetic field direction sometime around 2025. That 2015 prediction relied on an independent external reference point, data from NASA's Interstellar Boundary Explorer, or IBEX, a separate spacecraft orbiting much closer to Earth that maps the heliosphere's boundary indirectly from a distance by detecting particles called energetic neutral atoms bouncing back from the edge of the solar bubble. IBEX's observations had revealed a mysterious glowing band across the sky researchers call the ribbon, believed to trace the true orientation of the undisturbed interstellar magnetic field beyond the heliosphere. As Ed Stone, Voyager's longtime project scientist at Caltech, who wasn't involved in the 2015 study, put it at the time, the research offered a genuinely useful way to think about the data, giving scientists a concrete prediction for how much longer Voyager 1 would need to travel before finally reaching a region no longer strongly disturbed by the heliosphere's own influence. That 2025 target date, tied directly to a specific, externally verifiable prediction, is exactly what makes this such a genuinely testable piece of science rather than an untestable, purely theoretical debate. A second explanation focuses on something called magnetic reconnection, a well-documented physical process, also responsible for solar flares, where oppositely oriented magnetic field lines break apart and reconnect into new configurations. Researchers, including Michael Swisdak, alongside Drake and Ofer, proposed that reconnection occurring at the flanks of the heliosphere could create a complex, layered structure of magnetic islands, self-contained loops that allow interstellar plasma to leak into the heliosphere and solar particles to leak out, all while the overall magnetic field direction stays largely unchanged across the boundary. This model offers a genuinely different mechanism than simple draping, but reaches a similar practical conclusion. The region right around the heliopause is far messier and more permeable than a simple, clean bubble boundary, which is exactly why particle counts can shift dramatically while field direction barely moves. Ofer has since described this reconnection-based picture using an especially memorable analogy. Rather than a single, solid wall separating the heliosphere from interstellar space, the boundary behaves more like a series of connected tunnels or highways, allowing particles to flow in and out along specific reconnected field lines, even while the broader magnetic structure of the region looks superficially similar to what existed before the crossing. That mental picture helps explain something that would otherwise seem contradictory: how a spacecraft's particle detectors can show an unmistakable dramatic change, proving it has genuinely left the heliosphere's plasma environment, while its magnetometer, measuring a different physical property entirely, continues to reflect a magnetic structure still heavily shaped by the sun's own field. A third line of research from Nathan Schwadron and David McComas points to a more time-dependent explanation: coronal mass ejections, giant eruptions of material from the sun's surface that occurred during the sun's last period of high activity around 2012. According to this model, the pressure waves generated by these eruptions propagate outward through the solar wind and eventually reach the heliopause, creating alternating zones of compression and rarefaction as they pass through. Since interstellar magnetic field lines would drape differently depending on whether they're moving through a compressed or a relaxed region, this theory suggests some of Voyager 1's more recent, still shifting readings might reflect these passing pressure waves rather than a single, fixed distortion pattern. This time-dependent model is particularly notable because it directly addresses something the simpler, static draping model struggles to explain on its own: why Voyager 1's magnetic field readings haven't simply settled into one fixed, if unexpected, orientation, but have instead continued shifting and swerving over the years since the original 2012 crossing. According to Schwadron, by the time his original paper on the subject made it into print in late 2015, the field's measured direction had already swerved noticeably away from the orientation his own earlier model had predicted based on the IBEX ribbon, leading him and McComas to specifically investigate whether solar activity occurring years earlier could still be propagating outward and reshaping the local magnetic environment long after the fact. That's a genuinely different kind of explanation than either the draping or reconnection models, since it ties Voyager 1's ongoing, still-changing readings to a specific, datable series of solar events, rather than treating the boundary structure as a fixed, unchanging feature of space itself. It's worth being direct about where this leaves things. As Ofer herself has put it, boundaries that seem simple in textbooks turn out to be far messier in nature, and years after the original crossing, researchers are still actively refining their models to match Voyager's ongoing measurements, rather than treating the question as fully settled. A small but genuinely vocal minority of researchers have gone further, arguing that Voyager 1's magnetic readings are better explained by the idea that the spacecraft technically remains within some extended, unusual region of the heliosphere itself, rather than truly in undisturbed interstellar space, a minority position that most of the scientific community disagrees with, given the overwhelming particle and cosmic ray evidence pointing the other way, but one that hasn't been fully dismissed either. Even recent analysis, published as recently as 2025, examining the statistical structure of Voyager 1's more recent magnetic field measurements, has found that the field remains in what researchers describe as an intermittent, turbulent state, rather than settling into the smooth, predictable pattern a fully undisturbed interstellar environment would be expected to show, meaning that even now, well over a decade after the crossing, Voyager 1 may still be traveling through some kind of transitional, disturbed magnetic environment, rather than the true, pristine interstellar medium the original models predicted it would eventually reach. It's worth stepping back and asking why a decade-plus disagreement over magnetic field angles from a single aging spacecraft deserves this much sustained scientific attention. Because getting this right fundamentally shapes how humanity understands the true boundary between our solar system and the rest of the galaxy. Not as an abstract line on a diagram, but as a genuinely complex, physically real transition zone with its own internal structure, permeability, and behavior. Voyager 1 and Voyager 2 remain, to this day, the only two spacecraft that have ever directly sampled this region, which means every one of these competing theories has to be evaluated using an extremely limited dataset, gathered from just two specific trajectories through one specific narrow slice of the heliosphere's boundary. Any future mission specifically designed to study this region more thoroughly, something researchers have proposed but which doesn't yet exist as a funded, scheduled mission, would need to account for exactly this kind of magnetic complexity in its own instrument design and mission planning. This mystery also matters because the heliosphere itself functions as our solar system's primary shield against galactic cosmic rays, high-energy particles from deep space that can be genuinely harmful to biological organisms and sensitive electronics alike. Understanding precisely how, and how gradually, that shield's magnetic structure actually transitions into the wider galactic environment has real, practical implications for evaluating radiation exposure risks for any future deep space missions that might eventually travel through this same transitional region, whether crewed or robotic. There's a further practical dimension worth mentioning. This same boundary region also plays a meaningful role in shielding our solar system from a broader stream of galactic cosmic radiation that would otherwise reach Earth's vicinity in greater quantities. Some research has even proposed possible links between long-term variations in cosmic ray flux reaching Earth and the heliosphere's changing size and structure over very long timescales, tied to the Sun's own multi-billion-year journey through different regions of the galaxy. While that broader question remains speculative, it underscores that understanding the fine detail of how the heliosphere's boundary actually behaves isn't purely an abstract academic exercise. It connects to genuinely practical questions about the radiation environment our entire solar system exists within. There's also a broader lesson here about the nature of boundaries in physics more generally. The heliopause was, for decades, depicted in textbooks and illustrations as a clean, sharp line. Inside the bubble, outside the bubble, nothing in between. Voyager 1's magnetic field data has forced a fundamentally more nuanced picture, a boundary that's porous, twisted, layered with reconnection sites, and shaped by both the Sun's ongoing activity and the surrounding interstellar medium's own properties, none of which fits neatly into a simple diagram. That's a valuable, if humbling, lesson for how confidently scientists should expect nature's true boundaries to match up with the simplified models built to describe them in advance. It's also worth appreciating just how remarkable it is that this debate is even happening at all, using data from hardware designed and built in the 1970s. Voyager 1's magnetometer has now been continuously returning usable data for nearly 50 years, across a distance and environment its original engineers could never have specifically planned for. Every one of these competing theoretical models, draping, reconnection, pressure wave compression, has had to be developed and refined using measurements from an instrument never designed with this exact scientific question in mind, simply because no other spacecraft has ever traveled far enough to generate an independent, comparable dataset. That single point underscores just how much of humanity's current understanding of the true edge of the solar system rests on this one uniquely positioned, remarkably long-lived pair of machines. So here's where this genuinely stands right now. Voyager 1 crossed into interstellar space by every meaningful measure of particle density and cosmic ray activity on August 25, 2012. But its magnetic field data has never behaved the way scientists originally predicted it should at that boundary, and more than a decade of competing theories, draping interstellar fields, magnetic reconnection, solar-driven pressure waves, have each offered plausible partial explanations without fully, unanimously closing the case. A key theoretical model predicted Voyager 1 should finally reach the true, undisturbed interstellar magnetic field by around 2025. Whether that specific prediction has actually panned out, based on the most recent published analysis of Voyager 1's ongoing data, remains an open, actively studied question. Recent statistical analysis of the spacecraft's magnetic field measurements still describes the environment around it as turbulent and unsettled, rather than clean and resolved. That leaves us with a genuinely strange, still unfolding situation. A spacecraft, more than 25 billion kilometers from home, that scientists all agree has left the sun's bubble, still sending back magnetic field data that refuses to fully let go of the sun's own signature. Whether that's because the true interstellar field simply takes longer to reveal itself than expected, because the boundary itself is far more structurally complex than any current model fully captures, or because some entirely different explanation hasn't been proposed yet, remains a genuinely open question in heliophysics. It's worth remembering, too, that both Voyager spacecraft are running on rapidly diminishing power, with instruments being shut down one by one to conserve what little electricity remains, and engineers estimate their transmitters may fall silent sometime around the mid-2030s. That means the window for gathering more direct, first-hand data to help finally resolve this specific magnetic field question is not unlimited. Whatever final answer eventually emerges will very likely be built on the data these two spacecraft managed to send back before their power runs out for good. After that, resolving any remaining details of this mystery would depend entirely on modeling and indirect observation, without the benefit of a spacecraft actually sitting in the region in question. The real question isn't whether Voyager 1 has left our solar system. Every line of particle and cosmic ray evidence says it clearly has. The real question is why the sun's magnetic influence seems so reluctant to let go of the data, more than a decade after the spacecraft crossed a boundary that was supposed to leave it behind for good. If you want to be here, the moment new analysis of Voyager 1's magnetic field data finally settles this question, subscribe to the channel and turn on notifications. Because when that research comes out, we'll break it down here with the real data, not the invented version. One spacecraft, one boundary crossed, a magnetic field that still won't fully say goodbye. Whatever eventually resolves this question, it's worth remembering that it's being answered using data from a machine that has already been transmitting for nearly 50 years. From a distance nobody in 1977 could have confidently predicted it would ever survive to reach. Proof that some of the most important open questions in physics are still, quite literally, being answered in real time, one faint radio signal at a time. Thanks for watching.